Welcome back everyone. This video is going to be about modular exponentiation of large numbers. Large in the sense that it doesn't fit in the built-in data type, and it is the continuation of the last video of modular exponentiation. A raised to b can be represented as a times a, b for a b times, and here the constraint on a and b are such that a, b are less than 10 power 18 and m is also less than or equal to 10 power 18, and a and b are less than m. That's the constraint, and if looked carefully, 10 power 18 is generally will fit in 64 bits, but as the values of a keeps on increasing for the b times, this will lead, let's say, a times a, which will be 10 raised to 36. This may lead to overflow as more than 64 bits would be required to store the result. Application is making use of addition, and this addition will allow the answer to be fit in the 64 bit, and by applying modulus on that, the answer will not lead to overflow. That is the objective, and the approach has to be applied on the exponent part. So let's say a power, consider an example of a power 3 where a is multiplied for 3 times, and how the repeated addition method can be applied. Let's have a look. To make these examples easier, let's say that 2 times 2 plus 2, which is 8. So how repeated addition will work here? So 2 plus 2 will give us the answer. Consider this answer as capital A. This becomes capital A. Capital A times 2. So this has to be repeated for another capital A times. This is capital A again. And say B is 2 or 4. Let's say B is 4. And using the idea of modular exponentiation, and since this will be a very large number, this needs to be broken down in such a way that it addition of number a plus a plus a and so on a. This is a times, which is a times a, and similar for another a times a, this will be a plus a plus a. This will be repeated for a times. Now these two multiplication have been done, and result is, let's say, capital P and times capital P. So these two results, which is now of length 2a, has to be length 2a. So a plus a plus a, this will be of 2a times, followed by another set of 2a times addition. A plus a and so on till a. So a power 4 results in total of 4a times 4a times a. So this addition will be carried for 4a times. This is the, and everywhere the modulus has to be applied, and by the modular property addition, individual addition will be getting modulated. So a mod m plus a mod m repeated for 4a times. This will be repeated for 4a times. And then it mod of m. This is the result for even number. But what if the power was b, odd number? And that example has already been done. So this will be carried for 3a times addition. So addition, which is in turn used to calculate the value of large exponent number, given that a raised to b mod m can be written like a times b mod m, where b is a raised to b minus 1, and assume that b is 0, then the multiplication with any number results in 0. In case the value of b is 1, anything multiplied with 1 will give us the same number, that is a itself. But what if the b is even number? Then, as shown the case for a raised to 4, where 2a addition was taking at a time, and then 2 addition and for another a raised to 2 was taking place. Similar thing can be generalized in the recursive way, like binary multiplication of a b by 2 mod m plus binary multiplication of a b by 2 mod m. And similar thing if case b is odd, where b minus 1 by 2 will give us the value of even number, and plus a addition has to be carried, where a will be depending on the result of binary mult a b minus 1 by 2 mod m, and then a will be mod m. This is the recursive idea. Let us have a look